Now we've learned how to calculate energy, we're going to take our understanding a little bit further and put it into a realistic context. What you already know is that the amount of energy we put into any machine is never completely used for the job that we want it to be used for. There is a certain amount of wasted energy. And here's some pictures of some here. You can put 100% of fuel into a car, but only 20 to 25% of that energy is actually used for driving forward. The rest of it is actually wasted. 75 to 80% is actually wasted energy. When you're riding a bicycle, although it's much better, whatever you put into that bicycle, 95% of that is actually turned into forward motion energy, and about 5% of it is actually lost. In other words, riding a bicycle is much more efficient than driving a car when it comes to how much energy we use. So when it comes to us calculating the amounts of input and output in a system, we can then actually calculate how much efficiency a machine has. So the efficiency of our machine or our object is a measure of how much energy we actually put in and is transferred or transformed into useful forms. So in a car, we put in energy in the form of chemical potential energy, fuel, and the efficiency is measured by how much of that fuel is transformed into kinetic energy moving forward. If the energy is transferred out of the object, or it's transformed into a useless form of energy that can't be used for the job, then we call that wasted energy. And if there's an awful lot of wasted energy, we say that it's an inefficient machine. Now, every time we transfer or transform energy, we actually lose energy. We know that. So it goes to show that the more steps we have in any sort of process, like this one here, where we've got the chemical energy in coal being transferred into heat, which has gone to a motor, which goes to produce electrical energy, which goes to a transformer in our power line, which again goes through more power lines, back to another transformer outside our house, into our computer. Every time we transfer energy between any one of these stages, we actually lose some energy, which means we become more and more inefficient at every stage of this process. If you're asked to calculate how efficient your machine is, this is how you do it. The calculation is basically how much useful energy we get out compared to the original amount of energy that we put in. It's a fraction, and then we times it by 100 to turn it into a percent. So we're going to do a little calculation here which not only takes you through how to calculate gravitational potential energy of an object and the kinetic energy that it outputs, but we're also going to calculate how efficient that output is. So we're going to do an example now of calculating energy efficiency when we know how much energy input and energy output we have. Let's take our car, for example. Instead of $100 worth of fuel, we're going to think of it this way. If I put 100 kilojoules of energy into my car, and only 25 kilojoules of that energy came out the other end in the form of kinetic energy, that meant that 75 kilojoules of energy was actually lost in the form of heat and sound. If I want to calculate the efficiency of my car, then here is my calculation. My efficiency equals my input, which was 100 kilojoules, and the useful energy output, which was 25 kilojoules, times by 100 to turn it into a percent. So 25 divided by 100 is 0.25 times 100, which equals 25% efficiency. So realistically, I'm losing an awful lot of energy when I run a car. That's how you calculate energy efficiency. Here's some examples of energy efficiency of converters that we have around the home. Now, your normal incandescent light bulbs, not the energy efficient ones, they actually only transform 5% of your electricity into light. The rest is lost as heat. So they're very inefficient when it comes to using energy and converting it into what their job is, producing light. When you touch them, you'll notice they're extremely hot to touch. Most of the energy is lost. Normal electric motors run at about 80% efficiency around the home. A steam engine, all of that heat that you produce to make steam, only 40% of it goes into making the engine turn over. The rest of it is actually lost. Power station, the one that we saw up above, where we have the coal going to your home turning into electricity. This picture here, it actually runs at 30% efficiency. That means that every time we lose energy at each one of these stages, overall we lose 70% of the energy that was in that coal to heat and sometimes sound. We lose 70% before it gets to our home. That leaves us a total of 30% efficiency. And when it comes to us, the amount of food that we eat, 25% of it is put into useful energy and 75% of it is lost as heat and other things like sound. You might ask, why on earth are we losing so much energy? It's because every time something moves or transforms or transfers, we have a little friend called friction. Now, friction is our enemy and it's our friend. It's essential for us to be able to move and manipulate objects on this earth, but every time one atom rubs against another or bumps into another, they actually transfer a little bit of their energy to each other, and that means that we lose a little bit every time they touch. This causes transformations or transferals of energy, and it's usually into heat and sound. Now, unless you can then use that heat and sound for the job you're doing, it's essentially lost. Friction is everywhere around us. It's whenever we touch any surface, but what you don't realize is that even in the air we have friction. Every time you move through the air, you're pushing through air particles, and those air particles can actually steal away your kinetic energy. Think about it. If you stuck your head out of a plane, if you're going really fast, your face actually gets pushed back with the air particles pushing against you. When you're moving slower, we don't feel this as much, but it still actually steals our kinetic energy away. Also, whenever you're moving along a surface, whether it's the ground, walking or rolling, that ground is actually transforming some of your energy every time you touch and grip it into heat and sound. So you're actually losing energy because of every surface you touch, because of the friction between you and the other surface. So to finish it off, science has actually written a law about this. Now this is pretty big because laws do not come along often. They have to be proven. And most things that we know of today are considered theories, not laws. But the law of conservation of energy is pretty important. It basically states this, that all of the energy that was in the universe to begin with is still here, just in many different forms. It cannot be destroyed. All it can do is transfer from one object to another or transform. When we think of energy being lost in a system, say we're falling and we fall with 1,000 kilojoules of energy and we hit the ground, but at the time when we hit the ground we only have 800 kilojoules of energy with our kinetic energy, and our gravitational potential energy was 1,000, we didn't actually destroy 200 kilojoules of energy. We lost 200 kilojoules of energy in the form of heat and sound with the friction. So Energy is never destroyed. It's only lost to the system because it's been transferred or transformed into types of energy that we can't use for the job at hand. It's called the law of conservation of energy, and it's extremely important to remember.